The de Broglie hypothesis, proposed by French physicist Louis de Broglie in 1923, suggests that all matter has wave-like properties. This means that not just light, but even particles like electrons can behave like waves. De Broglie's theoretical proposal was based on Planck's theory and Einstein's relation. He could not prove his proposal by any experiment at that time. Later, photoelectric experiments and Compton effect were explained using de Broglie hypothesis. The first key concept of de Broglie hypothesis is wave-particle duality. This is the idea that particles like electrons can exhibit properties of both particles and waves. For example, light can behave as both a wave and a particle. That means light can act as a flow of photon. The second key concept is de Broglie wavelength. This is the wavelength associated with a particle and is given by the formula lambda equal to p into h, where lambda is the wavelength, h is Planck's constant, which is equal to 6.626 10 to the power minus 34 joule second. P is the momentum of the particle. The particle would have energy packets, momentum, wavelength, frequency, and amplitude. Let us look into derivation of de Broglie wavelength equation. As said earlier, de Broglie hypothesis is based on Planck's theory and Einstein relation. According to Planck's hypothesis, energy is quantized and can be expressed as E equal to h into nu, where E is the energy, h is Planck's constant, and nu is the frequency of the wave. Albert Einstein showed that the energy of a photon, that is a particle of light, is also related to its momentum p by E equal to p into c, where c is the speed of light. According to special theory of relativity, square of total energy equals sum of square of Einstein's energy plus square of zero rest mass energy. When the particle is at rest with zero mass like a photon, the first term mc square would be zero because m is zero at rest. Therefore, E equal to p into c or p equal to E by c, that is also equal to hf by c, that is also equal to h by lambda. Combining the two, for a photon combining Planck's and Einstein's equations gives h into nu equal to p into c. Since the frequency nu can be related to the wavelength lambda by nu equal to c by lambda, we get hc by lambda equal to p into c. Simplifying this, we find lambda equal to h by p. Louis de Broglie extended this idea to all matter, not just photons. He proposed that any particle with momentum p has an associated wavelength lambda given by lambda equal to h divided by p. Under wave-particle duality, the assumption is that particles can exhibit wave-like properties. Regarding momentum, for a particle with mass m and velocity v, the momentum p is given by p equal to m into v. To summarize, de Broglie proposed that a moving material particle of total energy E and momentum p has a wave associated with it, which is analogous to a photon. He proposed the relation between properties of the wave, frequency and wavelength with that of a particle like energy and momentum. The frequency and wavelength of a wave associated with a material particle of mass m moving with a velocity v are given by nu equal to E by h and lambda equal to h by mv. De Broglie referred to these waves associated with material particles as matter waves. The wavelength of the matter waves is now known as de Broglie wavelength, and the equation is known as de Broglie hypothesis. With this theoretical background, we shall do some exercises. Throughout the exercises, we will be frequently using terms like h, which is equal to Planck's constant, c which is equal to velocity of light, v equal to velocity of the particle, lambda equal to wavelength, p equal to momentum, E equal to energy, me equal to mass of electron, and mp equal to mass of proton. Exercise 1. An electron, a proton, and an alpha particle and hydrogen atom are moving with the same kinetic energy. Out of the 4 particles, which one will have the longest wavelength of the associated material particle wave? In this exercise, recall the formula for de Broglie wavelength. Lambda equal to h divided by square root of 2me, where h equal to Planck's constant and m is the mass and E is the energy. It is given in the exercise that A equal to constant for all 4 particles. Only mass of the particle is the variable in the equation 1. Among all particles, only electron is having the lowest mass. That is why electron will have the longest de Broglie wavelength. Exercise 2 is what is the speed of proton that has de Broglie wavelength of 0.08 angstrom. Note that de Broglie wavelength lambda equal to 0.08 angstrom, which is given in the exercise. Planck's constant h and mass of the proton are assumed to be known. According to de Broglie wavelength formula in the equation 1, speed of proton is equal to h by m lambda. Substituting the values in the equation 1, we get speed of proton equal to 4.957 10 to the power 4 meter per second. Exercise 3. If the de Broglie wavelength associated with an electron and a proton are same, what will be the ratio of their momenta and kinetic energy? Given that de Broglie wavelength lambda of electron and proton are equal, ratio of mass of proton to mass of electron is 1836, which is assumed to be known. From equation 1, lambda equal to h by p, where p is the momentum, lambda is equal to for both the particles, and Planck's constant h is also a constant. Only variable in equation 1 is momentum p, so the ratio of momenta should be equal to 1. From equation 2, the kinetic energy is equal to half mv square. On simplification, you will get kinetic energy equal to p square by 2m. P is also equal for both electron and proton from the above equation. The ratio of kinetic energy of proton to kinetic energy of electron equal to mass of proton divided by mass of electron, which is equal to 1836. Exercise 4. 2 particles have the same de Broglie wavelength and one is moving 4 times as fast as the other. If the slower particle is an alpha particle, what are the possibilities of the other particle? In this exercise, both the particles have equal de Broglie wavelengths, but the first particle is moving 4 times faster than the second. The ratio of mass of proton to that of electron is 1836. Lambda equal to h by p equal to h by mv as in equation 1. It is given in the exercise that lambda 1 equal to lambda 2. So m1 v1 equal to m2 v2. Therefore, m1 equal to m2 by 4. Note that the second particle is an alpha particle. The first particle must be either proton or neutron. Exercise 5. Find the ratio of de Broglie wavelengths of an electron and a proton when both are moving with A. Same velocity, B. Same kinetic energy, C. Same momentum in different cases. Find out which of the two will have longer wavelength in each case. Note that mass of proton is equal to 1836 times mass of electron. The de Broglie wavelength lambda is equal to h by p, where p equal to momentum and m equal to mass. The ratio of lambda e to lambda p equal to mp by me multiplied by velocity of proton divided by velocity of electron. It is given that Vp equal to Ve. Therefore, lambda E is lesser than lambda P. To solve the second part of the same exercise, use the formula lambda equal to h by square root of 2mk, where k is kinetic energy. It is given that Kp equal to Ke. Therefore, lambda E is greater than lambda P. To solve the third part of the same exercise, it is given that momentum of proton and electron are equal. That is, Pp is equal to Pe. Therefore, lambda E equal to lambda P. Question 6. An electron of mass m and proton have the same energy E. Find the ratio of de Broglie wavelengths associated with them, where c equal to velocity of light. For electron, lambda E equal to h by square root of 2mE, and for proton, lambda P equal to h divided by square root of 2mEp. Therefore, lambda E by lambda P equal to 1 by c square root of E by 2m, because Ep equal to Ae. Exercise 7. Calculate the momentum of photon having frequency 1.5 10 to the power 13 Hz. The value of Planck's constant h is assumed to be known. Given frequency equal to 1.5 10 to the power 13 Hz. Momentum p equal to h nu by c. Substitute the given values and you will get p equal to 3.3 10 to the power minus 29 kg meter per second. Exercise 8. A particle of charge q, mass m and energy E has de Broglie wavelength lambda. For a particle of charge 2q, mass 2m and energy 2e, calculate de Broglie wavelength. For any particle, de Broglie wavelength is given by lambda equal to h by square root of 2me. To calculate de Broglie wavelength lambda 2 for the second particle, substitute mass equal to 2m and E equal to 2e as it is given in the exercise itself. Therefore, lambda 2 equal to lambda divided by 2. Exercise 9. The wavelength lambda of a photon and de Broglie wavelength of an electron have the same value. Find the ratio of energy of the photon to the kinetic energy of the electron if m equal to mass of electron, c equal to velocity of light, and h equal to Planck's constant. It is given in the exercise that de Broglie wavelength of photon and electron are equal. The ratio of kinetic energy of photon to that of electron equal to hc by lambda divided by half p square by m. On simplification, you will get the ratio as 2mc lambda by h. Exercise 10. If the potential difference used to accelerate the electrons is doubled, by what factor the de Broglie wavelength associated with the electrons change? Note the formula between de Broglie wavelength and voltage applied to accelerate the electrons. Energy of electrons is influenced by voltage applied. In the equation, substitute new voltage equal to 2 times initial voltage. Hence, the new wavelength decreases by root 2 times. Exercise 11. According to de Broglie hypothesis, find the ratio of wavelength of an electron and that of proton having same energy E if m equal to mass of electron and c equal to velocity of light. Wavelength equal to hc by E, where h equal to Planck's constant, c equal to velocity of light, and E equal to energy. Wavelength of the electron lambda E is equal to h by p, where h equal to Planck's constant and p equal to momentum. Energy equal to kinetic energy equal to half mv square. Therefore, p square divided by 2m equal to E. Substituting the above values in the equation, you will find that lambda E equal to c square root of 2m by E. Hope you have got enough information now about de Broglie wavelength formula and how to use the formula in different scientific situations. We have reached the end of the video. Please do not forget to subscribe to the channel. Thank you for watching.